This video is geometric sequences as exponential functions. There's some vocabulary that you should write down. First of all, a geometric sequence is a set of numbers with a common ratio. An example would be the sequence 2, 6, 18, 54, and so on. The common ratio, instead of a common difference, the way we saw with arithmetic sequences, is because to get from one term to the next, you multiply. In this case, you multiply by 3 to get to the next term. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. The common ratio is the number you get when you divide one term of an exponential function or geometric sequence by the previous term. And the reason that we do division is because we're looking for the common ratio, and a ratio is a fraction. And so what you're really doing is taking each term and dividing by the term before it to get r. 15 divided by 18 is 3. 18 divided by 6 is 3. 6 divided by 2 is 3. So it is a ratio. An answer is 3, and it's in common. It happens every time we divide one term by the previous term. Below the blue line is the formula right here for a geometric sequence. This is the recursive formula. And if you remember, the recursive formula uses things like a sub n, which means a term, and a sub n minus 1, which means the term before it. You can see that we take this term before it, we multiply by r, the common ratio, and the answer, what it's equal to, is the next term. So remember that when you're looking at a sequence of numbers, if a sub n is some term in the middle, the next one is a sub n plus 1, and the one before it is a sub n minus 1. And so in between, these are just term numbers in sequence. Let's look at an example. We're given the sequence 2, 6, 18, 54, 162. We want to find the recursive formula. So to do that, you start at the end and you divide 162 divided by, we can even make a little division symbol there, 54. You get 3. And now you need to check. You can't just do one, because if you don't get the same answer every time you do this, it is not a common ratio, and that would mean it's not a geometric sequence. So you need to check at least a few. 15 divided by 18, we get 3 again. 18 divided by 6, we get 3. 6 divided by 2. So because we get the same answer every time we divide, the common ratio, r, is equal to 3. And that's your first step. You figure out, is there a common ratio? If there is, it's a geometric sequence. And so you tell me what r is equal to. If it's not, if these numbers didn't match every time you divided, you might look for some other pattern, like whether there's a common difference. Remember, subtracting every term minus the previous term. If you got a common difference, then this would be an arithmetic sequence. And you will have problems where you're going to need to decide. So it's important to know to try each of these. All you have to do then is plug r into the recursive equation. A sub n equals a sub n minus 1. Remember, you just copy the whole first part times, because now this is a common ratio, it multiplies from one term to get to the next term. And you just stick r in there. And that is your recursive formula for this geometric sequence. Pause the video now and you try the next one. How'd you do? I hope you divided, and I hope you didn't miss those negatives. Every time you divided, as long as you put in those negatives, you got a common ratio of -2. And so r is equal to -2. Notice that when r, the common ratio, is negative, our signs in each term flip-flop. It starts positive, then it's negative, then it's positive, then it's negative, then it's positive. Because when we multiply, moving forwards, by a negative, the positive number times negative gives you negative. Now you're starting with a negative, and when you multiply by another negative, you get a positive. And that's why it flip-flops back and forth. So an interesting clue to knowing what your common ratio is if you see a pattern that goes back and forth between positives and negatives, you're going to know that your common ratio has to be a negative number. All right, so all we need to do is plug it into the formula. I have a sub n equals a sub n minus 1 times, be careful, -2. How'd you do? Let's look at a graph and talk about this geometric sequence as a function, because that is what it is. Do you remember what the domain of a sequence is? Any sequence? I hope you said it's the term numbers, because that's x, your domain. The domain is the counting numbers. We have the first term, the second term, the third term, the fourth term, fifth term, and so on. The domain of any sequence is always the counting numbers. What about the range? Well, if you remember, as with an arithmetic sequence, the range of any sequence of any kind is always the sequence itself. And so our first term was 100, and our second term was 50, and our third term is 25. And then I had 12.5, and that's as far as they went there. The common ratio is 1/2, because if we look backwards, 12.5 divided by 25 gives us 1/2, and 25 divided by 50 gives us 1/2, and 50 divided by 100 gives us 1/2. And so once we find r, then if you're moving forwards, you would multiply that value of r. If we graph these, remember, each of these is an ordered pair, an x and a y. 100, 250, 325, and so on. You graph those points, and you see that they fall in what absolutely looks like an exponential curve. This one is decay, and I hope you can see that in this sequence the numbers are decreasing, so it makes sense that it would be a decreasing or decay curve. All right, the explicit formula. This is the second type of formula. We did this for arithmetic sequences as well. Remember that y is just like the a sub n, and x could be used in place of the n if we needed to write sort of a regular exponential equation. A sub 1, remember that's the first term. The sub number tells you the term number. R is the common ratio, and n is the number of the term. Doesn't this formula look an awful lot like the formula for the exponential function? Think about it now. Awfully similar, right? Instead of a for the initial value, we have a sub 1, the first term. It sort of makes sense. Initial value, first term. And instead of just having a plain x in the exponent, here we have an n minus 1. And we do that to account for the first term in the sequence. Since we don't start at 0, we have to sort of force it backwards. Let's take a look at how to use this. So here's just a copy of the formula. You should keep it on your page. It's the explicit formula for a geometric sequence. So here we have a sequence and we want to find the explicit formula. We find R. If it exists, we have to check it. This one is the same sequence we used before to find the recursive formula. So what's R? I hope you look back. You see it's 3. So R was 3. The second step, we can see in our formula we need R and we need A sub 1. These are the two things we need. We only fill in the ends if we're looking for a certain term, but if all we're doing is writing the formula, just like with arithmetic, we filled in A sub 1, the first term, and D. Here, the only things we fill in is A sub 1, the first term, and R. So A sub 1, the first term, is 2. And that's it. We plug them into the formula. So A sub n equals 2, the first term, times, and now R is 3, so I'll have 3 to the power of n minus 1. You can put the 3 in parentheses or not. The 3 is the rate. It is the common ratio. Go ahead and pause the video and you try this one on your own now. All right, how'd you do? I wonder if you noticed pretty quickly that this is the same one that you tried before to do the recursive formula. So now that you're doing the explicit formula, R is the same thing. You found out pretty fast once you started dividing. It's -2. And A sub 1, the first term was 3, and all I did was plug those in to the right places in the formula. This time it made sense to put parentheses around my R, and it might just be a good habit to do it all of the time, just in case. You don't want to miss your times and think that that's -2. It keeps it separate, makes it look a little less confusing. All right, so we have some points to make in summary. First of all, geometric sequences are very similar to arithmetic sequences, except there's a common ratio instead of a common difference. Also, it's important to start at the end and work backwards to find the common ratio. Recursive formulas just give the pattern to get from one term to the next. So while they look confusing, they really are just describing the pattern in the sequence. Explicit formulas look like regular exponential functions, and they work like them too. Some students have trouble deciding when they need to use the recursive and when they need to use the explicit, unless of course the question tells you which one to use. Use the recursive when you need the next or the previous term. As long as you know the pattern, it's easier to work forwards or backwards if you're only going one term away. Use the explicit formula when you need some random term number. Like if you need the 31st term, you're not going to start at the first term and work up 31 times. It's sort of a pain. So use explicit then. To use the explicit formula, you do have to know the first term and the common ratio. Don't forget, the domain of any sequence is counting numbers, 1, 2, 3, 4, 5, and so on, and the range is the sequence itself. We'll practice this more in class.